Hi, this is my first video in the Basic Math series. I'm going to show you how computers calculate exponents. In the first part, I will go over a quick review of perhaps what you saw in grade school. Then I will go over how to calculate real number exponents and the infinite sequences used to generate them. And finally, how to calculate integer exponents quickly. There are likely many more efficient ways to do this than what I show you, but what I do show you will get you there. I will also show you how computers calculate with very high precisions. Your calculator may only give you 8 or 10 digits and maybe a 2-digit exponent. I will show you how to deal with numbers much bigger than that. If any of this interests you, keep watching. So the first part of this is what you probably recall from grade school. An exponent, which is just an integer, is where you multiply the base by itself an exponent number of times. When you have two numbers that have a common base and each has an exponent, and you are multiplying them, you can just add the exponents. Likewise, if you are dividing one by another and they have a common base, just subtract the exponents. This is just a recap of grade school stuff. Now I'm going to introduce something you may not have seen. So now I'm going to introduce a formula that you may not have seen before. It is an infinite series expansion for the value e. E is a number like pi that never ends. Its value is approximately 2.718. Its value can be calculated by this infinite series. I'm going to show you two more functions. They are e to the x and the natural log of x. With a combination of these two functions, you can calculate the value of any value a to the b, where both a and b can be any number, not just integers. Here is how you do it. So I am going to use the function e to the x to calculate exponents. I mentioned earlier that the ultimate goal is to take any exponent to any base, where both the base and the exponent are real numbers. That is, they have both a decimal or fractional component that isn't zero. So it might seem strange that we're using functions that have exponents to calculate exponents, but note that both of the functions I have shown you are using whole number exponents, and any fractional value comes from division. We start off by saying that for some value a to the b, where both a and b are real numbers, they must equal the value, some value of e to the x. So a to the b is equal to e to the x. Now we also have a natural log function. We can take the natural log of each of these. So b times the natural log of a equals x times the natural log of e. Now the log to base x of any number x is always equal to 1. So the log to base e of e is also equal to 1. So b times the natural log of a equals x times 1. Now taking this result and then combining it with what we started with, we get a to the b equals e to the x, and finally a to the b is equal to e raised to b times the natural log of a. This is how to solve exponents. I will show you these functions using the programming language Python, but first I'm going to add a library to Python that lets me compute arbitrary precision numbers. Okay, so before I show you this, I will let you know that I have a soft link between Python 3 and Python. So when I type Python, I'm really running Python 3. So the arbitrary precision library for Python I'm going to use is called mpmath. You can check on your system to see if you have it by typing it at terminal. pip list pipe grep mpmath. Here my system shows mpmath 1.3.0. If yours doesn't give you anything, you can install it by typing on a Linux system pip install mpmath. I've already got it installed, so it's going to tell me that it's already satisfied. For all other systems, you'll have to use other means that your system provides for installing Python libraries. So now I'm going to show you how to use mpmath by typing a small Python script to calculate the value of e. You can calculate e by either solving the first function you see on the screen and its subsequent terms, or calculating the limit of the infinite sequence of the second function you see on the screen. This is a Python script that uses the method of the first function, that is, using subsequent terms. Okay, and I'll show you this just a little bit. This is the function, and what I do is I import mpmath. I set the numerical precision for mpmath. I also import sys. And then what I do here is this function, if you're not familiar with it, this is the regular Python that does basically this. And I'll show you this running. And here it's calculating e to 150 significant digits. Now I'm going to compare this. This is the method of the first function that I showed you. I'll compare it with BC. And this method will be using the limit method that I showed you. And it gives that. And these two values aren't quite the same. And I'll show you the difference between them. Okay, and so where all of the digits are zeros in the answer, that's where the two values agree, and everything else is where they don't agree. Adding more 9s and zeros to the function I sent, and that would be this function right here, would give you a better result. Remember this for later in the video, because I'm going to use this test when I write the final function and I compare the value that I get from the term limits versus the function that I create. Okay, I will point out one more thing about the program e.py. I don't have a set endpoint for this function. I use a while loop, not a for loop. But what I have is several variables that catch the state of the result. What happens is this: if you have calculated a value and its last digit should be, for example, a 6, and it repeats the next time as a 6, that's the last value, then the value isn't going to get any better and the iterating function can stop. If, however, the value is a 5, and then the function overcompensates and the last digit the next time is a 7, and then the next time through the function undercompensates and the last value, the last digit, is a 5 again, and the function will just keep running while toggling the last digits between 5 and 7. To stop this, I catch the states where if the last value is the same as the current value, then I stop. But also, if the current value is the same as the value 2 iterations ago, then also stop. So in this program, the variable result is the current value, old result is the previous value, and old result 2 is the value before the previous value. I will use this technique in most programs presented in this video. Okay, so now what I'm going to do is code these two functions, and that is e to the x and the natural log of x, as functions in Python. I'm going to do it first as separate pieces and then combine them together. Later I'm going to split the exponent into an integer portion and a decimal portion and calculate the decimal part separately from the integer part, and show you how to speed up the calculation of very large exponents. The first part I'm going to code is the e to the x part, and I've already shown you some of it. And here it is. This is the function. What I do is, I think I've already mentioned, I import mpmath. I set the numerical digits for mpmath. I also import sys. And then this, what I calculate here, this is the function, is basically all done right here. This is what would be normal Python, and this is the high precision math libraries. That's the direct equivalent. Okay, and I'll just show you it again for reference. And it calculates out to 150 significant digits. So now I'm going to code the natural log of x plus 1. Recall the log of x plus 1 is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5, and so on. Now here I'm trying to calculate the natural log of 2. I've coded this without using the high precision math libraries. I will show you why I'm not going to use it. As you can see, I've let it run. The denominator variable shows how many terms have been added, and as you can see, after summing over at this point more than 100,000 terms, we're only getting about 4 significant digits. So this function for finding the natural log of x doesn't converge very quickly. I will show you another function for finding the natural log of x. By the way, the poor function is called the Taylor series. Now it's also a Taylor series expansion for finding e to the x, but when calculating e to the x, the exponent converges quickly with about 1.5 times the number of terms to get the equal number of digits. So when calculating e, you have about 150 terms to give about 100 digits, or 300 terms gives 200 digits, and so on. So the Taylor series for finding e to the x is fast, and the Taylor series for finding the log of x is slow. So instead of using this expansion, I'm going to use the expansion you see on the screen. There's another part of calculating the natural log that I'm going to use. For values larger than 4,000, I will use a prescaler to calculate the logarithm, where the function I use is what you see on the screen. The natural log of a times 10 to the n is equal to the natural log of a plus n times the natural log of 10. This is a tautology which is useful because instead of dealing with a very large number, it gets scaled down to 2 smaller pieces, both of which are easily calculated and then added. So the combination of the 2 functions I have coded, the function to calculate e to the x and the function to calculate the natural log of x, will be combined to calculate the decimal part of the exponent. Just like what you see here with BC, the binary calculator, and here I'm calculating 3.25 to the 0.9267 power, and it gives you approximately 2.98. So now we have functions to calculate the decimal portion of the exponent. That is mostly what you came here for. But now I am going to show you a faster way to calculate the whole number part of the exponent. When you were in grade school, they showed you to just keep multiplying the base by itself over and over an exponent number of times. That works, but it's really slow. In computer terms, the algorithm runs in O(n) time. I will show you a method that lets things run a lot faster. First, I will show you one line of code that, if you aren't familiar with programming, might not initially make a lot of sense. X equals x times x. In grade school math terms, the only 2 values that make sense here are 0 and 1, but in computer terms, this line of code means something else. The values on the right side of the equal sign are the same initial value, and the value on the left of the equal sign is the result of what happens on the right side of the equal sign. So lines of code here are executed top to bottom if x to the first power comes in, and as a result of this line, x becomes x squared. So if you do this in a loop, the next time x squared times x squared on the right side gives x to the fourth power on the left side of the equal sign. The next time through, x to the fourth times x to the fourth gives x to the eighth on the left side of the equal sign. So the values generated in this loop starting from the first time are x to the first power, x squared, x to the fourth, x to the 8, x to the 16, and so on. 10 times through this loop and the exponent is over 1,000. 20 times through this loop and the exponent is over 1,000,000. And in general, 2 times 2 to the 10x is greater than 10 to the 3x for all x greater than 1. So 1,024 is greater than 1,000, 1,024 squared is bigger than 1,000,000, and so on. So at this point you are probably asking, okay, that's really nice for calculating exponents quickly, but what if I don't want an exponent that's 2 or 4 or 8 or 16? What if I want 38 or 15 or 12? So what we do is put the values into an ordered list called an array. One list for what the exponent is, and one list for what the base raised to the exponent value is, where both lists have a common index number. We will keep filling the list until the value of the exponent for the value on the list is the same as or bigger than the exponent that we want. Then we will stop filling the list. What we do then is go through the list with the exponents. If the value of that exponent at that index is less than the value of the exponent we want, we add it to the value, take the result from the other list, and remember to multiply it, and repeat that through the list until we have gone through the list, or until the exponent we have created is equal to the exponent we want. Here's a program I have written to show you a better example, but written without the high precision math. So now I will give you an example that hopefully makes things a bit more clear. The exponent we are looking for is 15.23 to the 98 power. At this point, we have already split the decimal from the integer part of the exponent. We will combine them later by adding the exponents and multiplying the common base to each exponent result. So this is the program that I've written. As you can see, it starts by showing you the filling of the list, 15.23 to the first power, giving you this. Then the exponent doubles in the next term on our list, and 15.23 times 15.23, that is x equals x times x, gives us this. So each value here multiplied by itself gives each subsequent result in this list, and the exponent keeps doubling every time, 1, 2, 4, 8, and so on. Once we've gotten to 64, 64 times 2 would be 128, and that's larger than 98, so we don't include that term. So that's where our list ends. Our list is then filled. Now that we've got the list, we start picking through the list and creating our exponent 98. So we go through the list. 64 is the largest number that we have. It's less than 98, so we use it. 15.23 to the 64th power gives us this. So that's our preliminary result. Okay, and it's 4.9 to the 75th power. The next item on the list is 32. 64 plus 32 is 96. 96 is less than 98, so we use this term. So 15.23 to the 96 is our first value. 4.9 to the 75th power multiplied by 7.0 times 10 to the 75th power gives us this. So what we do is we add our exponents, 64 plus 32, giving us 96, and then we take the product of the base 15.23 raised to the exponent, this, multiplied by each other. So the 64th power and then the 32nd power giving you this. So this times this gives this. Okay, then we go through the next item on the list. That's 15.23 to the 16th power. Now, 96 plus 16 is too large. 96 plus 16 is 112. It's larger than 98, so we skip over this entire term. The next item on the list is 8. 96 plus 8 is 104. That is larger than 98, so we skip over this term as well. The next item on the list is 4. 96 plus 4 is 100, which is larger than 98, so we skip over this term also. The next item on the list, 15.23 to the second power, 96 plus 2 is 98. So we use this term, 96 plus 2 is 98. That's the exponent we're looking for. We take the last value we had, 15.23 to the 96th power, take this value, multiply it by this value, giving us this value. Okay, so what we've done here is we've just cherry-picked through our list and created the result that we want. Once I've got an extra efficiency in this, so once we've gotten the exponent we want, it just skips over all of the other values in the list. The only value we had in the list left over was 15.23 to the first power, but it skipped over it anyway. If the initial exponent we were looking for was something like 64 or 32, what you would see here, because of this efficiency, is only one term on the list followed by nothing else. It would skip over all of the other terms in the list. What we ultimately did is what you see on the screen. Remember, when you have a common base, you can add exponents, and when determining their value, you multiply. The terms we used are 64, 32, and 2. It skipped over 16, 8, 4, and 1 because adding them would have resulted in a bigger value than 98, which is what we wanted. So because we have a list of easily precompiled values, we just see if the sum of exponents is less than or equal to what we want, which we did, and then multiplied. This is a lot faster than calculating the way you did in grade school, where you would just calculate the base by itself 98 times. In terms of computer runtime efficiency, it's O n log n. So this program is the result. It's called exp.py. It's the equivalent of adding the integer and decimal parts of the exponent. Remember, they have a common base. And then I just take the product of the base to each part of the exponent, multiply them, and you get the result. I will show you an example of calculating a large exponent with this program. And here, the first number that I give is the base, and the second number is the exponent. And it takes just a moment to calculate. And so this is the result. This is what you gave it, just repeated back to you. Then it's 4.68, and this is times 10 to this power is the result. And now I'm going to show you something just a little bit smaller and use it as a comparison. I have to cut back the size of the values I'm giving because even high precision calculators might be more limited than what I have created. In the case of it's an online website, I'm using it to compare. If you give it a very large exponent beyond what my program will calculate, it just returns infinity. So I'm just going to use a slightly smaller value. And again, the first number is the base, and this is the exponent I'm raising it to. And this is the result, 1.9 times 10 to the 998,952,458th power. Now you might be asking right away, is this the correct answer? Well, we can do at least a comparison with the online source. I have a website that can do high precision calculations, and I will put in the same values I tested with here on the local program and compare it with what they generate, and then put the two values into a test file and compare them, and I'll show you the results. Okay, so now what I'm going to do is put the same values I tested with on the local program against the online source, which is what you can see. And what I'm going to do is then compare the two values that I got and see how the two results compare. Okay, here I have put the two results into a file. The top results here are from the web source, and the results on the second line are from my local program. It's a bit hard to see because I put all 150 digits on a single line for each result to make it easier to compare them. The online source calculates to fewer significant digits, so the exponent appears just a little bit earlier, but the results are the same. And I'll just scroll and let you see everything. Okay, and the results, as you can see, are about the same. Now we will do one more test. If you recall, I showed you an infinite sequence for calculating e and then showed you a limit for calculating e. We will use the program we created using the limit function and compare how it does against the value of e generated by the sequence function. Okay, so the first program calculates e by using terms, and we'll run that now. And this is the value that it generates. And we're going to more or less assume that the value that this generates is correct, because adding terms gets you to e very quickly and very easily. Now what we're going to do is compare it by using what we ran, the program we ran, and using infinite sequences in series, that is using the limits of a term, 1.09 to the 99th power, and you start off and it's not quite the right value. It's 2.6 instead of 2.7, so right off the bat it's wrong, but it's a limit as it hits infinity. So what we can do is make a much better value by, instead of using 1.01, we can make it a much better value and using a much better exponent, 1.00, a bunch of zeros, 1 raised to the 999 power, and you can see that this gives us a much better value. Instead of 2.6, it gives us 2.7. And you can do a side-by-side comparison and subtract the value we got from the first from the value we got in the second place, and where you have zeros is where the two results agree. And so here we have quite a few significant digits already. If I added a lot more zeros and a lot more nines, it would be a lot better. Okay, so the reason I haven't used BC, the binary calculator, for comparison of large exponents is because it doesn't seem to use exponent accelerators. If you give it a very large exponent, like what you've seen me do with the other program, like this, your computer may appear to hang. And if you look in the process tree on your computer, you will likely see the program BC using 100% of the CPU, and it might stay like that for a while unless you stop it. That's why I can't use it to show you the calculation of very large exponents. So at this point you might be wondering, is there a maximum that you can enter using my program and this library? And there is. It's not insurmountable, it's just a current limit as to what you can do. When you enter more than 4,300 characters in the base, or when you enter more than 4,300 characters in the exponent, the library will give you a runtime error. The error gives you hints as to how you can pass this current obstacle, but as it currently exists, this is the upper limit. When I started this video, I mentioned large exponents. Hopefully you aren't disappointed by this upper limit. Also, I don't have any way of testing the numerical accuracy of the results when you're at the limits of the library. If you happen to have a supercomputer with a high precision math library installed and machine cycles to burn, maybe you can do tests against my program and get back to me. It seems to give correct results against what I can test, but I suspect that at the extremes of the library and program, errors might start to creep in. Not on the entire answer, but starting at the digit furthest from the decimal in the base of the answer and getting closer to the decimal as extremes are reached. Again, everything might be completely correct right to the end, but I have no way of testing it, so use it with care. Anyway, here is the extreme that I will show you. And it has 4,300 characters in the base and 4,300 characters in the exponent. And it runs just like this. And it gives you the result like this. And it's 1.0 times 10 to the 4291st power raised to the exponent 1.0 times 10 to the 4291st power, 1.06 times 10 to this exponent, which is quite large, is the result. And I can show you how many digits are in that exponent. There's 4,296 characters in that exponent. And now I'll show you what happens when things go wrong. I'll add an extra 9, and then I'll run the program again, but this time it'll have an extra 9 in the base. And what you get is this. Value error exceeds the limit 4,300 for integer string conversion. Value has 4,301 digits. This is maybe a better view of it. Use sys.set_int_max_str_digits. So it's turning this into a string and it's trying to convert it, and that's just on the base, and it gives you the same error when you exceed the value in the exponent. So that's the problem, and that's what the limit is on this program. Okay, another thing, in the program I have written, note that it can accept fractions for both the base and exponent like this. And you can also give it values from a bash script like this. Okay, and if you give it exponents like this, okay, what it normally does is it will display the base and exponents in the answer exactly like this. But if you give it a large exponent, first of all a large base like this, and then also give it a large exponent like this, it will show you this instead. Okay, so in this video I showed you how computers calculate real exponents. First I showed you how you can calculate the values of e to the x with an infinite sequence. Then I showed you how to calculate the natural log of x with an infinite sequence. And for that I showed you a slow version and then a fast version. Then I showed you how to combine e to the x and the natural log of x to calculate real number exponents. Then I showed you how to calculate integer exponents quickly. And finally, we add the exponents the integer and decimal parts make together to get the final result. I finally showed you a few tests on our results against other arbitrary precision calculators on the web. I have tried to be complete while also perhaps being a bit terse to get the ideas across quickly and also not including any 16-week course. I hope this acts like a primer on how it's done and gives you insights on how the sausage is made. The results I get with BC, the binary calculator, and likewise the online precision calculator websites agree with the results I get, and I don't know how they make their sausage. It could be very different, but the results seem to be the same as what I get. Having said that, I haven't tested this program in all respects very thoroughly, so be careful how you use it. Hopefully this video gives you some insights in calculating exponents. Thank you for watching. Thank you for watching my video. If you liked it, please click on the like and subscribe buttons just below. I really appreciate it. Also, if you want to be notified of when my next video drops, click on the bell. I'll see you in the next video.